Hey everyone, my name is Ashley, and today I'll be walking you through question 4, graphs from the balanced search series and tries CSM worksheet. So in this question, we're given a pseudocode algorithm called graph search, and we have to answer 2 questions about it. So before going to the questions, let's walk through the pseudocode. So in the function graph search, we're given 2 parameters, start and fringe. And we can figure out more about what those variables do more as we go on through the pseudocode. So the first thing we do is we create an empty set called scene. So let's draw a scene. It's so it's pointing to some kind of like list or array or some kind of like data structure that contains other data structures. And we see it add it calls an add function which adds certain fringe. So based on that, we can assume that fringe is also some kind of container. And then start is being added to it, so start is inside the container. So I'm going to write start inside the box just to make it clear that this is the item inside. And then so we have a while loop. So while fringe is not empty, do, and fringe has start in it, so it's not empty. So we want to go inside the while loop. It goes in node, and we want to create a variable called node, and we want to remove the fringe and put it into node. So we want node to point to an item pop from fringe. So node will be pointing up, but essentially be equal to start. And since we're moving from fringe, it's no longer there. And we want to check if node is equal to goal. So if it is equal to goal, we return node, which in this case is start. If not, we go on with the function, and then we check if node is not in scene. Scene right now is empty, so we want to go into this if statement. And in this if statement, we have another add function. So we want to add node to scene. So this will be being put in scene. And then for every child in neighbors node, we want to add to fringe. So we want to put like node neighbor 1, essentially like node neighbor 1, node neighbor 2. Sorry, this is kind of messy. But hopefully you get the idea that fringe is some kind of like data structure that like contains like both of these. And we'll do that for every neighbor node. And then since fringe is, we'll check if fringe is empty again. If assuming node has neighbors, it is not empty, so continue on with the while loop. And eventually, if we ever hit the condition that fringe is empty, which makes it exit the while loop, it returns a failure. So hopefully that helps you understand how this graph search pseudocode is working. So the first question is, in the given graph search pseudocode, why is it necessary to keep track of a scene set? So we see we're creating a scene set at the very beginning, and we use it when we go on. So let's pretend we didn't create it, it wasn't in the function. So we go to called graph search start fringe, we add start fringe, and then we check while fringe is not empty. So we go on, we move an item from fringe, put it in node, check if node is goal, assume it's not, so we continue on with this function. Eventually we get to node is not in scene. But since we don't have a scene set, we just ignore this if statement. We just immediately go to the case that it of what is inside the if statement. So we want to add the node to scene, and we have for every single neighbor node we want to add it to fringe. So now we're given a very simple graph here. So let's say we're given a graph with 2 nodes and 1 edge. So pretend we call the graph search with starting with this node, and then we go through the while loop and everything. And eventually, when we're adding, when we get to this step, or we're getting a step where we like supposed to like add a scene, and we like don't, we eventually go to the for child and neighbors. We want to add the child to fringe. So right now, fringe is empty because we just popped start, so fringe would have like neighbor. And so we want to run this function. We want to add neighbor to fringe, and the while loop is string is not empty, it occurs, and then we want to run it again, and node is now equal to the neighbor. And so we do option checks on the neighbor, and you should see that like at this point we search all nodes, so it should be done. However, the neighbor also has its own neighbors, which is the original start. So we end up adding the start back to and having a loop like that. So it'll create an infinite loop, which is why we need to have a seed set to prevent us from looking at vertices that we've seen before. So let's just say to prevent infinite loops. And the second question asks us to give a tight asymptotic runtime bound for BFS and DFS on the graph G equals VE. Okay. So let's pretend we have a graph that looks like this. So, and we run BFS starting from here. So if we run BFS starting from this node, we'll have to check you'd have to check like all of its neighbors. So when the first time you run it, you have to check this vertex and check all its neighbors. And then after searching both of the neighbors, you want to check each of those like nodes neighbors that it hasn't seen before. So it just keeps going down. It looks like this. So usually it's like this search will terminate after it checks every single vertex in the worst case. In the best case, it'll stop at this like the start is that goal and we stop there. But worst case, we look through every single vertex and it's a failure. So we know one of the things that will be included in runtime bound will be the number of vertices, or like which is basically when given set V, set of all vertices, that denotes the symbol denotes the number of items. And however, this is not it. When going through every single vertex, we also have to. This is only in the case that there's only like one vertex going to each other vertex, and there's no like cycle. So the number of edges will also play into account. So even you'd have to search every single edge from every single node. So even if it's seen before, you still have to check the edge because you have to go through the for loop. And so on. So you have to check every single edge as well. So it's a number of vertices plus a number of edge, and this creates a asymptotic runtime bound of number of vertices plus number of edge, or like number V plus number E, which is this. Hopefully to help you understand this question more. And see you guys next time.